Hello, everyone. So, as you might have gathered from the questions I just asked, I'm kind of into queuing. And I'm also the shared cake maintainer, and this work is an attempt to do something a bit similar to what we just saw in hardware level, actually, to scale software rate limiting across CPU cores using a single cake instance. Multiple cake instances, but sharing some state. And this is joint work with Jonas, who's a student at TU Berlin, and I will just hand it over to you.
Okay, perfect, thank you. So let's dive in with a little motivation. So as we have seen, network speeds are just surpassing CPU speeds. And this makes software rate limiting especially challenging, and we need solutions to scale this. And especially what we are focusing on is to enforce a global rate limit on a network interface. And the existing QDisks in the kernel, they cannot keep up with these network speeds, and especially they don't scale due to the root QDisk lock. So here we have to show this a little bit more. Here we see the scaling behavior of HTB and cake with the configured global rate limit of 20 gigabits per second. And on the x-axis, we have the number of transmission queues. And not only can we see that both queuing disciplines cannot even achieve rates near 20 gigabits per second, they also decrease their performance with the increasing number of transmission queues due to lock-on tensions. And a couple of years ago, we have seen a solution, the EDT BPF approach, which was also presented at this conference. And this was a great solution for rate limiting multiple flow aggregates on end hosts, but it has its shortcomings when it comes to enforcing a global rate limit. This is because the BPF program will set a timestamp for every packet that it sees, or it sets the departure timestamp for every packet. And when we have a global rate limit on an interface, then this timestamp will always continually increase, which will build a virtual FIFO across all transmission queues. And this has negative side effects on latencies. Also here a little motivation to this. Here we see the EDT BPF approach a little bit modified to enforce a global rate limit. And one thing we can see there is that it can achieve these high rates of 20 gigabits per second in this case, but also the orange line here, we can see that the FIFO is building up, which really increases queuing delay. So what we are going to present is MQ-Cake, which is a multi-queue compatible variant of the QDISC cake. And we will show that we are able to enforce high rate limits while keeping the queue smart and thus keeping latencies low. So the rest of the talk is structured as follows. First, we go a little bit into the design of MQ-Cake. Then we go over the evaluation and all our experiments we conducted. And then we give an outlook on our future works, and also Toke will present the upstreaming plans. So let's start with the design. Here we have a high-level overview of the architecture of MQ-Cake. We have the MQ QDISC at the QDISC root, and then a cake instance attached for every hardware queue. And we connect these cake instances with a linked list, which we need to synchronize state between these instances. And the algorithm follows a simple principle. We scan over this linked list in certain intervals, and this interval we are calling the sync time. And during the scan, we will determine, or a MQ-Cake instance will determine if another QDISC is active or not. And based on the active count of their siblings, we take an heuristic approach to calculate the local rate limit for one MQ-Cake instance, which is just the global rate divided by the number of active QDISC we found. When do we consider a QDISC active? This has 2 points here. One is that another QDISC is active if it has packets enqueued, and if it has sent packets out since the last scan, which is similar to a heartbeat signal. So now the question is, how does this perform? How does it work, or how does it perform? In our experiments, we have 2 servers connected back to back, and one server is generating the traffic and measuring the throughput, and the device under test is enforcing the global rate limit and forwards the traffic back to the traffic generator. So in the first plot, we have a comparison between single QCake, HTB, and MQCake, and we are interested in the rates that MQCake can enforce. And we can see that MQCake is able to achieve rate limits up to 24 gigabits per second and probably beyond, but we were capped with our hardware capabilities. And on the other hand, Cake and HTB, they plateau at around 8 to 9 gigabits per second. This plot shows the deviation from the configured rate. And here the take-home message is basically that MQCake is able to have a relatively low latencies or deviation of 0.2% from the configured rate, while single Q and HTB, they just go off the charts beyond 5 gigabits per second. The next interesting question is, how is the scaling behavior of our approach? And in this case, to really show this, we reduced the packet size to 64-byte packets, and we measure the throughput depending on the number of transmission queues. And we can see that MQCake is able to scale linearly, but the slope reduces after 20 transmission queues, which is because we are using hyperthreads at this point. And there will be some resource sharing between execution threads. And looking at latencies, here we have the latency plot from the EDT BPF test case we saw in the beginning. And we can here see that, as shown already, EDT BPF approach has delays beyond 1 second, and this delay is correlated with the drop horizon that can be set for this. And MQCake can achieve very low latencies compared to this, which is below 0.5 milliseconds at the 99th percentile. But of course, our approach, or current approach, is not without its limitations. So far, we have only looked at very static traffic patterns, so we didn't have really a change in the number of active queues. And here we see such a switching event on the left side, where we switch from 4 to 40 active queues. And in the top, we see MQCake is configured with a sync time of 100 microseconds, and you will notice the spike, which is due to the fact that the MQCake instances are not yet synchronized, and they will have an inaccurate rate estimation. To take this to the extreme, we can see in the top below, in the plot below, the sync time with 100 milliseconds, and you can really see that this spike even more than doubles, and the width of the spike is closely related to the sync time. So what we learn from this is that we can lower the sync time and achieve higher accuracies. But we cannot go arbitrarily low, as we can see on the plot on the right side, where we can see that if we choose very, very low sync times, we will observe an overhead due to the scanning. And the more QDisk we have to scan, the worse the overhead is, and thus we achieve lower throughputs. Another problem that occurs are imbalances, which occur that when some MQCake instances are undersaturated and cannot even achieve their estimated local rate limit. And we can see this here in this dip in the plot around here. And we can also see that if we're lowering the sync time, we can somehow counterbalance these imbalances in load. But as we have seen in the previous slide, we cannot go arbitrarily low with the sync time. Nonetheless, we think we have a promising approach to synchronize state across queues. And in the future, what we want to look at is to improve the imbalancing issue. We have already experimented a little bit with implementing some rebalancing between queues, which seems feasible. Definitely mitigate the overshoot during the switching events. And the traffic we have tested this with is very synthetic, so also see some performance under real-world conditions would be very insightful, and determine or finding ways to determine the sync time automatically so that nobody needs to configure that by hand. And now Toke will go into the details of our plans to upstream this work.
Yes, thank you. So the current implementation, we just did modifications solely to the cake QDisk and had its ini function just walk the QDisk tree and build this data structure of sibling QDisks that it's walking. And for upstreaming purposes, this is not necessarily ideal. It's a bit too much sort of information about the underlying QDisk structure that to put into the QDisk itself. So we're sort of proposing a more general API where we have a separation of concerns between the MQ QDisk, which is what installs multiple QDisks, and then shared cake, which runs with this in this sibling mode. And basically, it's an API where a parent root QDisk can allocate shared state that can then be shared between siblings. And it's more or less short enough to fit on a couple of slides. So I just took the bits of the patch and put it here. And basically, if you look at, we have this new struct QDisk shared data, which we put in a list in struct QDisk, which becomes the sibling list. And in QDisk opts, a QDisk can set this shared size if it wants to use this, in which case it also needs to set the shared assign and optionally the shared init functions, which will then cause this when a QDisk instance is created, as we will see on the next slide. This is for shared MQ. When in MQ graft, which is where a child QDisk is attached to shared MQ. I'm omitting a few details. You can look at the full patch there as well, but MQ graft is one of the places where this happens, also in init. If the sub QDisk here, new, has a shared size set, it will allocate one of these shared struct, shared data structs, and then it will assign it to the child QDisk. And then it's up to the child QDisk to figure out what it does with it. So in this case, for shared cake, the shared struct just contains a list head where it will do this linking of siblings that it can walk, as Jonas just explained. And this shared get, the new ops here is the key. So the shared state is keyed on the QDisk module implementation using the ops pointer in this case. So in this instance, every instance of cake under one MQ QDisk will get the same shared state pointer. But if you have two interfaces with two MQ QDisks that all have a couple of cake instances underneath them, they will get a shared instance per physical device. And this means that shared MQ sort of defines what is the notion of siblings, and then it's up to the QDisk implementation to support this, to figure out what does a sibling mean for me. And for cake, in this instance, that means we will scale the weight across it. So that's sort of our proposal for an API for this. I will, unless someone yells loudly now, I will post this in RFC after the conference, and we can discuss it. But that's sort of our proposal for how to upstream this. And of course, we want to do some more real-world experiments before submitting a proper patch, but that's sort of the idea. Yeah, questions, comments?
Great presentation. I have a question about the name, MQ Quake. Why Quake? I mean, it's a generic infra which should work with any child, like children above, like below MQ, right?
Yeah, so the shared API will be generic across QDisks. The reason we call it MQ Cake, it's MQ-aware version of shared cake that we did the experiments with, but we're not calling it MQ Cake when we submit it.
Oh, okay,
yeah.
That's fine. Just that.
We got plenty of time, so. So, can you put back your data structure again? The shared one. So there's a bunch of ref count. There's a ref count there, and you say the lock. You didn't show any parf data. Do you have any parf data? Or it's the lock, right? That's killing you.
It's just a setup.
Yeah, this is just the setup. So shared MQ keeps, the ref count is to keep track of how many cake instances do I have under me for shared MQ. So it didn't necessarily need to be a ref count T. This is not used in the data path at all. This is just the setup.
I see.
So it's up to the QDisk just gets a shared state, and it's up to the QDisk to do any synchronization needed to access the shared state. And for shared cake, it's all read-only in the data path, so it just walks the list of sibling QDisks, and that's RCU protected. So it's, and then during the setup, it's RTNL protected to add one.
So I have another question, because you set up the thing at a QDisk level, so there is no way HTB can one day use that. Because HTB, you would like to have, let's say you have 16 queues. Ideally, you would install 16 HTB, and then have some shared data, but for all the class of HTB class, not QDisk, the whole QDisk. Because like a BWE enforcer at Google, we want to control destination, not global rate on the NIC. That is not useful for us. So we would need some class, per class, shared info.
But yes, so I did have the HTB use case in mind. So the fact that it's the parent that decides what siblings means in its context means that we could move this struct list head shared state into the MQ private data, and then HTB could do it's the same thing between states, but still have the shared init and shared assign for the child QDisk be the same, right? I think. But yeah, I'm not totally. I finished figuring out how to use this with HTB, so ideas definitely welcome. But I did think about sort of if you have, say, an HTTP tree with 4 classes with a cake instance that should share bandwidth in the same way, it should be able to say, oh, I will assign shared state for the 4 sub-QDisks of these 4 classes in the tree, and it should work the same way. And from the other side, from the child QDisk point of view, the API would be the same. You just get a shared pointer, and you say, okay, this is shared state across instances, and I will use that the same way, regardless of its...
So before EDT time at Google, we tried something similar, but at the HTTP layer. And so instead of having some sync agent doing sync every 100 milliseconds or 10 milliseconds, 1 millisecond, we just grab tokens in batch. So we had a sharded HTTP and the ability to grab token, but instead of grabbing tokens packet by packet, like be able to grab the equivalent of 60 packets or at a time. So it was reducing the fault sharing on the shared info without any lock. Of course, we were using atomic operation, and that was good enough at that time, but that was clearly a good amount of work compared to ADT solution.
Yeah, right. So the trouble with this is that cake is not token based. It also sets timestamps, but I did think about batch allocating tokens as well. So this becomes like the modification to the data path of shared cake, which we didn't show here, is quite small. It's just resetting its rate, which makes this easy to implement.
Again, I think this infra should be orthogonal to Quake. I mean, it's just think about making more generic things instead of just trying to expand Quake.
Yeah, but that's why this makes it up to the child QDIF to decide how it's going to use the shared state. So if it's token-based, it can do batch. It can just put an atomic variable in the shared state and do batch allocations from that. And if it's time-based, like Cake, it could do the QDIF walk, or maybe we can, if we come up with a better solution as well. I did think a little bit about sort of the generics. That's why this API is there. But if you have other sort of specific child QDIFs that you want to implement this for, please let us know, and we'll try to keep it in mind to get the API fleshed out.
You didn't show how, so you had, if you go back to some of your previous slides where you're showing the scaling. Yeah, like, actually, yeah, go backwards, yeah. Maybe...
This one?
Yeah, that one is fine, I think. The question is, so you're showing the number of transmit queues, but how are you tying the queues to a CPU, or how many CPUs did you have on this thing?
Yeah, we have 40 cores, including hyperthreads. And we configure the receive side in a way that we can we send a certain number of flows, and we then distribute the incoming flows equally across the receive queues. And thus we can control how many cores are active on the transmit part. Yeah.
Okay, so the transmit and receive on the same, or bound to the same CPUs?
Yes, yeah.
Okay, and which driver is this?
I think I40E.
I40E, so the transmit completion and receiver, there's only one interrupt there, I think, right?
Yes.
Okay. Thanks. No questions? Okay, we still have like 10 minutes. We can take an early break, or...
Wait.
Are you testing UDP FLAD for? Because I don't understand why the BPF thing was so bad. Like the HTTP, right? BPF based HTTP.
Yeah, this one you mean?
Right.
Yeah, it's because it's forwarding packets. So
it's forward. But but like the sender doesn't respond to like congestion signals, or like if it's what is it running? It's not BBR, right?
So it won't send any ECN signals or something like this. It will only react to packet drops, and if the drop horizon is 2 seconds, as it was proposed in the presentation a couple of years ago, then we just build a queue which is big enough to hold packets that have a value of like 2 seconds delay, basically.
Right. So the sender is just like sending packets and not responding to.
No, this is TCP cubic.
But so you are sending at for the UDT case at a higher rate than line rate, because otherwise the queue cannot build up. So I don't understand.
No, so it's not ADT BPF on the host that is this TCP sender.
Yes, but what's the difference between shaping in MQ or ADT? Is it the same rate? I don't see how it can build a queue.
It's configured, so it's configured to the same rate, but and I think we raised the queue limit of the underlying FQ scheduler. But
so on the MQ case, you are dropping packets. That's the reason why you don't have the...
yeah, you have flow queuing on DQ, and you have an AQM and MQ cake, whereas with ADT BPF, you're just setting timestamps, and it becomes a FIFO.
Do you want to say anything about how fair?
No, it's not a FIFO. I'm sorry, it's not a FIFO. It's a FQ. It's a fair queue.
Yeah, but it becomes a FIFO. I can link you a blog post that explains it. But basically,
I know. I know
yeah.
pretty well how FQ works. I wrote it.
No, but it's not queued as a FIFO. But because it's a shared, the on ingress, there's one state variable that says the next timestamp for the next packet that comes in, which is shared across all queues. That's how you get the rate, right? So you have packet comes in, and you say, this is the next timestamp for the packet. Next packet comes in, you advance the same timestamp all the time at in queue.
That's the EDT program, right?
Yeah,
It's not part of FQ, this part. It's the
No,
BPF program.
it's not FQ. That's the EDT program. So the EDT program ends up building a sort of, I call it a virtual FIFO, because you keep advancing the same timestamp and you don't react to, like you do this at in queue, so you don't react to the queue length when you do this. You just keep advancing.
Well, you do
this
whatever
info.
you want. It's a BPF program, so it's programmable.
Yeah, sure.
So if you prefer to drop, just drop.
Oh no, you could, but
So
that's
not
not what
pretend-
EDTF. But that's not what any of the EDT BPF implementations do today.
So sorry, no, you are wrong. You don't know how companies are using BPF.
No, but
It's
any
not
of
public code.
any of the open source EDT BPF implementations, including the one that was at NetDevConf.
It's templates.
Work this
It's
way.
purely templates. You are free to
Sure,
adapt the code.
no, but yes, you could implement something different, and Cake is something different, so it's a different implementation. Right?
Yeah, but I mean, that's...
No, you could totally do something different for EDT BPF.
If you want to
yeah.
drop packet, drop, but that's not the same effect than just delaying the send time. It's
No, true.
something,
No.
it's different goals.
But there is this place where, because you take all the decisions on in queue, you cannot change that decision after the fact. Once you've in-queued the packet, you cannot go back and change. So you cannot do the FQ-cuddle flow queuing.
You can, you absolutely can. You don't have to update the timestamp in the future if you don't want.
No, but then you're not enforcing
can
a global.
drop instead.
But then you're not enforcing a global rate.
You can, you absolutely can.
Okay, so you in-queue 10 packets, set their timestamp.
It's like the TPF token bucket. You have a token bucket.
No.
Once you exhaust the credit, you drop.
Yes,
so if
you
prefer
can
to have
drop
a
packets.
Smaller bucket, you just
you
make it
you can
smaller.
drop packets, but you cannot reorder them in the queue after you have in-queued them.
But what's the point?
That's what FQ-cuddle
You are
does.
forwarding, so if you don't want to...
No, this is the new flow optimization in FQ-cuddle, right? So you in-queue 10 packets, packet 11 comes in from a different flow, and you want it to go to the front of the queue. If you do that, you can do this with EDT by not setting a timestamp on that packet, but then you will go over the configured rate because the timestamp is what implements the rate.
No, you can just have different... So, okay. So I think you're mixing things. At Google, we don't use a single token bucket in EDT. We have different bandwidth enforcers. So you can have reorders, absolutely. It's not part of the FQ or whatever, it's part of your program.
Sure, but then you are enforcing a rate per traffic class or per
That's
flow.
exactly what what we want to do.
Yeah, but that's not what we're doing. We're doing one global rate for a
But you
an
did it
interface.
wrong. I'm just saying that. So that's
No,
fine.
like the use case for Cake is forwarding on home riders, right? You set one rate on the
Perfect.
interface.
You can implement that in EDT just fine. You don't have to pretend it's going bad. It's just the way it is. That's all.
Yeah, we're not saying that it's impossible to do something different than
You are
EDT.
comparing something with a template, which is obviously not meeting your needs, with something else. So that's obviously not.
Yeah, but let's. I would like to hear from you. Let's do that offline. But how you would do this in EDT BPF? Sure.
We still have time. Anybody else? All right, I actually like that exchange a little bit.
No, I'm enjoying it.
Okay, thanks. Let's give them a hand.
All right, thanks everyone.